Hello, good afternoon everyone. Welcome to Liquid Brain. So today we're going to talk about how to run some basic statistical analysis in R. So hopefully it wouldn't take more than 15 to 20 minutes. And there's three main learning objectives. So the first one is some data exploration. How do you load the data? How do you see the data? How do you select a certain columns from a data frames and so on? And how do you find a mean and median? So the second one will be three different types of analysis. There'll be some correlation analysis, some regression analysis, and some comparison analysis. So there will be some Pearson correlation, regression analysis. Specifically, we're going to run a linear model. There'll be Ttest and ANOVA. And lastly, we're going to run through very quickly on some visualization result, particularly on Heatmap, some clustering analysis, and PCA, which is principal component analysis. Okay, so what is this video for? So this video is not for people that are very familiar with the R scripting environment. If you are, you might not need this video to run it. It's for very basic level, and it's for people that doesn't really know how to use R to start with. Okay, so I'm also not going to be talking too much about what statistical analysis is about and what does each of them do. With that, I actually included one of the link over here, which I think can really help you to decide what kind of statistical analysis you want to do. And a lot of statistic is not really like a rocket science. There's no specific task for a specific thing. It's always about art and about how you want to interpret the data. So you can have the same data interpret in different way and come out with different kind of perspective, and that is perfectly acceptable in the world of research. And most importantly, understand what you want to do with the data and start with an objective. Okay, so what is parametric task, regression, comparison, or correlation? So if you're not familiar with what is parametric versus non-parametric, a non-parametric tasks are usually data that are not very clean, like a small set of data, basically like social research science data, like wage income data, data that doesn't actually follow a certain normal distribution. So they're strongly skewed to one side or another, or it's just very messy data. So those are called non-parametric tasks. So non-parametric tasks is not as strong in terms of the conclusion and concluding power compared to parametric. So we're not going to talk about those tasks today. We're just going to assume that the world is ideal, the world is great, and your data comes in a very nicely distributed format, and we have a large amount of them. So that's why we are talking about regression, comparison, and correlation. So what are they individually? So correlation is to check whether two variables are related, so without assuming cause and effect relationship, while regression is used to test for cause and effect relationship. And the main difference between the two of them is that correlation simply tell you whether they're correlated or not. But regression analysis is able to come up with a model or an equation that you can use for the prediction if you have new data coming in. So it's a little bit stronger in terms of regression. So the third one, of course, is comparison, which is pretty straightforward. So the most famous one is called the student Ttest, where I'm not too sure about the origin, but how I understand it is that if you have two classes and they both take the same exam, are the means of the two classes significantly different from each other, which is why it's also very commonly called the student Ttest. I'm not sure that's the origin though, so don't quote me on that. So before we go to R, so just to make sure that you are able to understand the way that I write my Google Slides, everything that I include in the later slides, if there's two hashtag sign in front of it, it's a command. So these are just something that I wrote. Do not run it, it will not run. It will not run in our environment. Everything that preceded by a larger than is the code. That's the actual code that you want to copy into the R environment. Lastly, the underline is usually the output. And before we start again, let's look into our data set. So we're gonna again use the Iris data set. It's very famous, it's very popular, and have been used everywhere. So we have a characteristic of three different types of flowers, Centosa, versicolor, and virginica. And we have sepal length, sepal width, petal length, and petal width. And three species of flower, 150 of them, 4 type of characteristics. Okay. So first one, data explorer in R. So how do I import the Iris data set into R? Very straightforward. When you open R, it looks like that. What you do is just type Iris and press enter, and you'll be greeted by the 5 columns that we have showed you just now, as well as the species. Okay, so what I usually like to do is to is to pipe the iris data frame into a new object called iris. So in this case, it allows me to see a value on a data here in the global environment. And when I click on it, I'm able to have a spreadsheet view of them on top, so I can have a clearer idea of how it looks like when I'm trying to code, I'm trying to do things in my console. Okay, so the second one is to select one of the columns. So we use the $sign, fairly straightforward. So you just type iris in your console window, select the $sign and go to petal length, and that is where you get 150 value over there. So we can also do that by piping the data into a new, well, I shouldn't call it piping. We are assigning the due data into a new variable called x over here. And when you run it, it won't show any output, but on top of the global environment here, it will actually show you a value called x with 150 different numbers. So these numbers are the 150 petal sepal length that we have selected earlier and being assigned to x. So once we've done that, we can also just type x, press enter, and be able to view that 150 different values that we just assigned to. Okay, so once that's done, let's go into mean and median. So how do you run the mean and median is pretty straightforward. So the mean of x, just type mean, open bracket, close bracket, and put x in the middle. Enter, you got 5.833. And if you want to run the median, just type median and x, you get 5.8. So all these are pretty straightforward. Okay, so the next one is correlation. So how do you run Pearson correlation is, again, pretty straightforward. The function is called COR. And for those that are new to the R environment, what you can do is that if you want to know more about a certain function, you can just type COR and then just type R, and these guys also have documentation. Okay, so this will have the official documentation from the R and the comprehensive R archive network, the CRAN basically, showing you that what do they do and what kind of thing you can change. Okay, so I'm gonna leave yourself to read more into that. So what we usually do is to just go back to the slide, copy the whole thing, and this we are comparing the two different data sets from sepal length compared to their petal length, and we want to see if they are correlated in certain way using Pearson method. Okay, just press it and sorry, you might have to change the double quote here because I don't know why some encoding issue that doesn't recognize. So you'll be greeted by the output, which is 0.87175338. So what this means is that everything closer to 1 means they're strongly correlated positively. Everything near to -1, that's negatively correlated, but they're strongly negatively correlated. Negatively strongly correlated. They're one of them. And everything close to 0 means they're not very correlated at all. Okay, so what you also want to do, instead of actually just get the 0.87 and call it a day, is also plot out the data and understand that does it look like a correlated data or not. Then this will be able to tell you. Remember, there's also 3 species here, so most likely they would be correlated, but not that much. Okay, so interspecies maybe. So next one we're going to do is after we've finished done the correlation, we want to create a linear model because the model kind of looks like a linear relationship, not a log, not an exponential, so on. So we want to run a linear model. So the equation for linear model is just Lm, x, y, the data equals to data set. Okay, so data equals, don't change that, only change the name of the data set to your data set. So I've include an example over here where model is assigned as Lm, petal length to sepal length. So we want to compare the relationship between petal length and sepal length. Remember, R exists, Y exists in the back, and data is equals to the iris data that we run just now. So what we do is that we copy paste this in, and you will actually see a new object called model, which is a list of 12. You can actually click in and you can see all the individual breakdown of the model. So just to get a more simple idea of what it is, you can actually use another function called the summary function, and this will actually just give you a more simplified output of the summary of the analysis. Okay, so let's look into this analysis a little bit over here. So you can see that we can actually see our formula that we used previously, and we can actually see the residual, coefficient, significant codes, which is whether it's significant or not, and we can see all the individual details they want to look at here. So there's something that I actually just realized is what is the meaning of the where is the thing that I'm trying to say? There's a R square value and a P value. So the difference between R square value and P value is that R square value actually measure how far the data is from the line that you draw, while P value justify how generalizable your data is to the populations. Okay, so if you don't really get what I'm trying to say, you can actually read from the few where they are included. Here. So you can actually read about the correlation here in the notes in the slides, and you can also read about the linear correlation here where included in the slides. It's a bit, I don't want to make this video another a 1 hour video again, so maybe we'll come back to this when we have more time. So, but basically that is how you run a linear regression model very easily, and you can get your intercept and you can get your gradient. Okay, so you can get the intercept in here, and that's your M and C. Where is it? M and C here. So y equals mx plus c. Your gradient is your M and C is your intercept. So you can actually get your linear model quite easily based on the summary output that you got just now. Okay, so it's also generalized. It's also advisable to try to plot the line up just to check if the concept is correct. Where we have slightly low R square value. Our R square value is only around here, 75%. Or 76% without adjustment, but our p-value is quite high. As you can see, most of the data is not actually very near to the line, which is why we only get about 75% of our square value. Okay, so that's basically a linear model, and you can see that the intercept is actually -7, which is not drawn here, and our gradient is 1.85. And if you don't understand what is appline is just the way that how we draw the linear line over here. Okay, so let's just try that again. When we plot, it will show a plot without the line. But when you actually run appline based on this linear model, it actually draw your linear model directly out on the plot. So that makes it easier to understand what we're actually trying to do. So let's move on to our third agenda, which is the comparison, a t-test. How to run a t-test in R. Actually, again, very straightforward, just t-test data 1 and data 2. And of course, the problem is that how do you prepare data 1 and data 2? Because first of all, you need to understand t-test compare data in different groups. So what we need to do here is to separate data 1 to only contain Sentosa flower, and the data 2 only contains Virginica flowers. So what we do here is use an equation called subset, which is able to select only the first 50, which is only select the data where the flower species equals Sentosa, and subsequently we are doing it for data 2, which only select flower with the species Virginica. Okay, so let's just copy this and we get our data 1 here. As you can see, there's 50 of them. And data 2, we actually can select data 2, and you can ensure the data is correct by looking at here, or if you want to visualize data again, you can also type it in quite easily. And we run the t-test on the 2 data like that. Okay, so this is a Welsh t-test. So let's go back to our slide for the example here. So this is a Welsh 2-sample t-test, and the most important things about the t-test is to just look at the p-value, and our p-value is actually quite low. It's actually 2.2 to the power -60. So we can actually quite confidently tell that these 2 samples has a significant difference in their petal length. And that's basically, and this your confidence interval, and with 95% confidence. So again, you can find the notes I'll add more description about what is t-test in the Google Slides later. You can find it down there when you go and click on it. Okay, so the next one is actually ANOVA. So people always ask what is the difference between ANOVA and t-test, and to put it simply, ANOVA is able to run more than two sample set. Again, it's a massive, what is that called? A massive simplification. And if you do want to know more about what's the difference between ANOVA and Ttest, you can actually go to this website over here, Scribble. I don't want to put too much, otherwise they will copyright strike me or something. But I will put their link in the Google slide over here. Please do go and have a look on what is the difference between one-way ANOVA, two-way ANOVA, and when to use Ttest and when to use ANOVA. So to actually run ANOVA, we're going to use a function called AOV, which is actually analysis of variance. And the data structure is similar to the linear model that we ran just now, which is data 1 to data 2, and with data is equal to data set. So what we tend to do usually is to again run the function and pipe and assign it to a new object called AOV model. So we can do that, and you can see your model showing up as a list of 13 with all the individual calculated parameters here. And what we can do is that again we use the same method, which is summary AOV model, and this will give you the significant level, the comparison between two groups. Okay, so you can see this is the same things that we are running just now. So we have species, the degree of freedom is 2, and again we are looking at our p-value, which is -2 to the power of 16, and you have 3 asterisk over here, means our confidence level that these two are significantly different. These two groups of data is significantly different from each other is 0.001. So we're quite confident that this would never happen by chance. Okay, so we have done all this thing. It's actually very important to understand a little bit about data visualization because to be honest, this is not interesting. People look at this data. It tends to get a bit tiring when you are looking at data tables all day. People like to look at figures and so on. And I believe Heatmap is one of the really easy way to do it, and you are able to show a lot of information very, very fast and very, very easily because it has multiple dimensions on it. Okay, so we're using something called a Heatmap library. So how do you install a library is that you go to package, install, and type in Heatmap. Actually stands for Pretty Heatmap, and you just press install, and that would install the library into your computer. And what we do is that we're going to run this, what is that called? This function, which actually generate the heat map that you see on the right by selecting the first 4 columns in the iris dataset, and we want to cluster the rows and cluster the column using a complete clustering method. Okay, so what does that allow? I haven't loaded into my environment. I haven't installed. Well, the problems are multiple computers and sometimes things happens. Okay, so again, run this and do an environment, and we run the function again. So this will generate heat map on the sepal length, sepal width, sepal width, and petal length again. Okay, so we can see that sepal width and petal length are more closely related to another in terms of their behavioral patterns, while sepal length is the furthest away from all the 4 parameters, and you can see how the sample groups together and from one another based on the clustering method. Okay, so just an example, understand when to use it and depends on the size and type of the data that you do. Okay, so the next one, the last one we're going to run today is actually principal component analysis. Again, principal component analysis is very useful when you have multi-dimensional data. Let's say you have a 600 dimensional data. So that's data with 600 different columns. You want to know which few are the most important and which few are very similar to one another. You want to throw them away before you feed into your machine learning algorithm, or you just want to know what are the most important columns that I need to analyze. PCA is able to do that. Okay, so we're using 2 libraries called FactorMyR and FactorExtra. So follow the same method, just install the library into your environment. This actually might take a while because our FactorExtra and FactorMyR is actually a very, very big library that's actually very useful in a lot of different things rather than just PCA. Okay, so we do the same thing about library, which is just load the library of FactorMyR and FactorExtra into the environment. And we're able to run our PCA using a function just for PCA. Okay, again, we're just gonna select only the first 4 variables because they're numerical and everything, and the 5th column, which is species, we want to throw it away. and the rest you can actually remain as default or try to change around and see what happens. Again, if you need documentation, just go and type the name of the functions and just run CRAN documentation. That should give you a breakdown on how do you able to navigate around the functions. Okay, yep, we are almost done there. And if you're wondering why are they installing so many packages, because they are actually dependencies. When they code one of the package, actually depends on multiple package that are multiple simpler package, and they will actually install all of them together. So that's why you get so many things getting installed on your computer, and sometimes it's bigger and sometimes it's smaller. It depends. Okay, so just load the library into your environment, and we can run our PCA analysis, which we assign to another new object called iris.pca, and it will actually show you a PCA graph of the variable. And yeah, you can see that sepal width is very far away from the other three columns, and you can also try to find what is that called? FVIS PCA individual means they want to plot individual flowers as their individual points, and we can color them based on their species. So you can actually see that based on dimensional 1 and dimensional 2, versicolor and Virginia are slightly closer to each other in terms of their flower patterns, while Setosa is actually quite far away from the other two species. So it's very easy to separate out Setosa from two other species using whatever algorithm that you can, but these two will have a slight overlap on whatever algorithm that you want to have, whether it's neural network, SVM, random forest, or any other kind of thing that you want to run to separate the classification of the tree of the flowers. Okay, so you have something very similar to this if you run it, and if not, leave a comment down below. We can see what happens. So for those that make it to this far, thank you very much. I hope you enjoyed and you learned something. And just to make sure that you know that you have learned something, please go and do some. I've prepared a Google form just for you to check if you are able to get what I'm trying to say, and please run it on your own computer in R, and then if you get a result, then you get a result. If not, then maybe watch the video again or watch some other video that I have. For now, I hope you have enjoyed the video. We'll see you in the next one. Bye.